Okay. So a couple of quick announcements for logistics before we continue. Grading is unfortunately still in progress for your midterms because I had to enable a beta feature on Gradescope and it took an extra couple of days. That won't delay any subsequent assignments, just had to be enabled once by an actual living human being. Strange as that may sound. Minor issue, but a couple of days delay. It should be done by tomorrow night. I was hoping to have them done this morning. Didn't quite happen. Your first assignment will go live tonight. Feel free to take a look at it, but don't worry too much about starting because you're going to need the material from Thursday as well to do it, relating to this week and last week's material. And then on Thursday, the first reading and writing assignment will also go live. And those will be due not terribly soon, so don't worry too much. But those will be going live to get a sense of what you're going to be doing on those. Okay, so let's pick up where we left off with our chronic commitment issues. No, which register is free at commit? It's the overwritten register because it is no longer in use. But you know that it cannot possibly be in use by anything else at this time. Okay, let's just walk through some more renaming examples. You went over a few of these in recitation on Friday, so I'm not going to dwell laboriously on these. But if here was our load word, pulling P4 off of the free list to write the new version of T0, updating T0 to now point in P4, right? And reading P1, which was unchanged, S1, P1 still there. Okay. Then the next one, right, would look like this, right? So the next add into T0 would pull an entirely new register off the free list for its name. This will disappear in a second. Look up the current values of T0 and S2 in the map table. And note that it in fact overwrote P4, which was the old value of T0. Okay. Now store word does not write anything, right? Store word does not write a register. So it does not need a register from the free list. So it's going to read the current value of S1 and T0, grab those and produce. I tend to note that the box with X in it just to keep everything nicely aligned, but a whole lot of nothing there on the overwritten. So some record indicating that there is no overwritten record. Okay, same with sub. The sub's going to grab the next thing off the free list because it does in fact write something. And look up the current values of S1 and S2, grab those, and there you go. Boop. Keep updating the map table. All right, so this is very mechanical, which is why you're going to be programming. Right, that's going to be part of your first programming assignment. You'll be doing some renaming. Okay. Similarly, the immediates, we never need to do anything about those. We had them here before. They don't need renaming. -4 is -4 is -4. Rinse, repeat, rinse, repeat. Branch, like store, also does not write a register. So these are all reads. Okay. Now let me ask you a different question. Let's say that the contents of the free list had only been up to P6. What would have happened? What if I didn't have P1 through or P4 through P8 available? What if I had just had P4 through P6? What would have happened when I tried to rename the ADI? What are the resource dependencies of rename? Yes. No, it would just wait. I mean, it would eventually take, P3 is presumably what would actually then, yeah. Yeah, we would wait until something was returned to the free list from commit, right? And then take that, but it's going to stall. So the free list can have underflow, right? This is a finite length list, right? For the purposes of class, we are not showing you the 256 length free list and giving you enough instructions to have it run out, but it can run out, right? There are a finite number of these available. That is one potential resource limitation. In practice, usually, hopefully, things are being returned at about the rate that they're being consumed. This is not always the case. There will be some fairly long stalls, right, that do happen. You have a load that's at the head of the queue, goes all the way to main memory, bunch of stuff's going to pile up behind it. You can't actually run out of these resources. Okay. Let me ask you a different question. If I was doing this 2 at a time, so same, ignore our free list limitations, same free list that we had before. If I was doing this 2 at a time, or 1 at a time, or 3 at a time, would I end up with any different renamings? Would I have chosen the same set of registers if I did this 2 instructions at a time, or 1 instruction at a time, or 3 instructions at a time?
I mean, if you're doing like the first same time, have like a, I mean, have readout, right? They'll have people.
Yeah. Yeah, so there's some additional complexity in being able to do that, but I would have actually arrived at the same set of renamings, right? This is all happening in order. So the application of architectural to physical register mappings is done in order. And the effect of this renaming is the same if I did this 1 instruction at a time or 3 or 4 instructions at a time, right? The logic and the priority encoders that are going to have to handle figuring out that I have both used, renamed, and used, and right, are going to take a little bit, but they don't affect what the actual outcome would be. Yes. They do. Yeah. So the outputs all have different names. Right, so every time I define an output, so this is, what this basically gives you is this is T0 version 0, right, was in whatever it was to begin with. T0 version 1 is now in P4, T0 version 2 is now in P5. I basically get versioning across my physical registers. Yes, because this instruction is in fact dependent on the load word. Yeah, that dependence is real. Yeah, so we want to keep the real dependencies. If we just wanted to like remove all the dependencies and execute all the instructions at once, I mean, it wouldn't be your original program, but you could, you know, you're welcome to try. Yeah, now we need to keep the read after write dependencies that are actually there, right? It's the resource naming dependencies via the output registers that we're trying to get rid of. Okay, so our code example, if we look at this after renaming, right? And again, this is only 1 copy of the loop. This is just unrolled dynamically. This is not actually unrolled by the compiler. This is dynamically a trace. Just want to make that clear in your head, right? So they're not actually 2 copies of this load word instruction in the program. This is 2 times that I have fetched the same instruction, 3 times that I fetched the same instruction, and so forth. Right? One of the nice things about dynamic scheduling is that it can look across whatever window it has until it runs out of resources, right, to try to find that parallelism, however many times the loop was or was not actually enrolled by the compiler, modulo its ability to correctly predict these branches and fetch the right instructions. Okay. Okay, so read after write, they're all still there, right? War? War? No, we have defeated war. Yes, I know it's been a year in the Ukraine, but we have defeated write after read. Right? So count your minor victories where you can get them. None. None. We're good. All right, so all of our register carried anti-dependencies are gone. Right? Renaming has accomplished what it set out to do. Okay. And all of our read after write dependencies are preserved, right? Because every time we went to look up a value, we went to the map table and said, well, where is the version of T0 that I'm actually dependent on? It's whatever the current naming is in this order. That's why this all has to be done in order, why it's going to be identical no matter how wide your actual machine was. Right? The only thing that's going to be different is the timing. Okay. Questions so far about renaming? Okay, so fetch and decode were the same as before, so we haven't really touched them. Renaming, we've now covered. Let's wander into dispatch. All right, so dispatch is a new stage we have not seen before. And dispatch's goal is going to be to move our renamed instructions from the in-order part of our machine into the out-of-order data flow execution engine in a way that encodes enough information to commit them eventually in order. right? So basically to set up all of the structures and entries that are required, right, in these various buffers here, so that this logic can do what needs to be done. Okay? And they'll have, just as with rename, right, although it's not shown here, we'll bring it back in a number of slides. There's also a map table sitting around here somewhere, right? There's some additional auxiliary structures that are in use. I won't draw them all, but dispatch has some of those of its own. Okay. The dispatch is the last in order piece of this front end of the pipeline. So let's go. If you were going to split your load and store instructions into an effective address computation and just a load or store access, you would already have done those by the time you get to dispatch. We're not belaboring this at the moment. We'll give you some more examples of that later. But basically, you just need one additional virtual address computation register, and the rest of it's an add immediate instruction. Okay, so what do I need to do? So I need to populate these various structures with entries, right? So one of these structures is the issue queue, right? The issue queue's job is to actually do the scheduling of instruction itself, right? This needs to be accessible both as a RAM and a CAM, right? So how many people are familiar with content addressable memories? No? Okay. So let's pause here for a second. I think I have another slide just doing to the side, but I'll do it in advance anyway. So a random access memory, I provide you an arbitrary address within the space that it covers. It provides the contents back to you. Ideally, if it really is a true RAM, then the behavior is relatively uniform across any address in that space I give you. Real RAMs tend to have a little bit of non-ideal behavior, but close enough. Content addressable memories, I give you a value, and you, depending on the structure of the memory, tell me whether the value is present in the memory at all, or usually equivalently from a hardware structure, light up the location within the memory where that data actually is, right? So for instance, a CAM may in fact have multiple locations within its memory that light up on the same value. If I store 5 different values at 5 copies of the same value in 5 different places in a CAM, I ask it for where this copy of this value is, it should give me up to 5 responses, right? Again, depends on what you're asking it about. Are you asking it presence? It'll collapse that down into an OR of all those bits. If I want to do something based or to all of those entries, I need to actually know where they are, right? And maybe actually give me the addresses out. We'll talk a little about the implementation of this in a bit. The long and short version is that content addressable memory is more expensive than random access memory. This should not be surprising, right? There's some comparisons that are happening here versus just a lookup. Okay. The other structure that I need to populate is the reorder buffer. This is what is going to hold all of the instructions in their original program order until commit. Right, this is what allows us to preserve our in-order semantics. And every entry in the ROB is going to have to keep track of all of the intermediate state that is going on in this instruction, right? So it's going to need to be able to support recovery. So for instance, if I want to unroll and go back and return my setup to its previous state, I'm going to need to unwind my changes to the map table. That's one of the reasons, in addition to freeing things, that I'm keeping track of the overwritten register, right? So all the recovery structure, all the metadata, right? Everything is going to be there in the ROB, right? And finally, we have another structure just for loads and stores, right? So again, loads and stores are a little bit different than things that are touching registers because we renamed all of our registers. We did not rename memory, right? We did not statically version our memory with an indirection table. You can try to ponder for yourself how difficult that would be in practice to actually do, right? And we still only have one memory. So we actually still have yet to be understood dependencies that will dynamically arise between our loads and stores. We have a separate structure just for handling the fact that the loads and stores may be dependent on each other in ways that we don't fully understand. Again, we don't fully understand it because we haven't computed the addresses yet. Right? If I knew what all of the addresses were, then I could do all sorts of fun renaming, I could do all sorts of fun versioning, but the addresses are dynamic, so good luck with that. Right? So separate structure. Okay, so what information am I going to need to broadly be holding in my issue queue? Right, so the issue queue has a bunch of entries. Right? The issue queue doesn't have to be strictly ordered. Or in fact, it really, in practice, will not, because it's going to fragment very quickly. I do want to keep track for starvation and other sort of, sane scheduling purposes of how old the instructions are. But that's more of a post facto priority arbitration later. Yes. So the age is really just to break ties for readiness. So in the issue queue, you could have 8 instructions that are ready and only be able to support issuing 3 in a cycle. So which 3 do you choose? You would want to clear it as fast as possible. So I'd want to prefer the older ones. You could have a more complicated policy as well. So for instance, if we were fast forward to next Tuesday and we get to simultaneous multi-threading, you might also have some policies based on which thread they came from. So this is basically a policy piece. All the rest of your logic will work even if you don't have the age. It's reasonable to assume that there is some sort of prioritization metadata there as well. So you can think of age as the proxy for any prioritization metadata that you want to put in there. In contrast, just before we go forward, this has to be FIFO. Your ROB must be FIFO. This is where order is preserved, right? So this, the age of it is implicit by the ordering within the ROB, right? Okay, but in the issue queue, this is going to basically be an associative structure, right? So the ordering is quite weak, right? The entry does not mean anything, right? Things are going to be scattered wherever there were free available slots in the issue queue. You just put stuff in. Okay. So this is basically a set of pieces of information, each entry. And you can think about the physical structure of this in a bit, because this is going to correspond to a physical structure. Right? It's going to have some physical layout. But I need to keep track of what the instruction is that I want to do, i.e. what functional unit does this need to be scheduled onto? Is it an add? Is it a multiply? What are you? What operands does it require? Right? There could actually, in fact, be up to 3, although one of them would be an immediate in that case, right? But without loss of generality, you can think of these as your register operands, source 1, source 2, right? And it's going to have a ready bit. Has this actually been produced yet? Right? Because we don't know, because they're going to get executed in whatever order that it is available. So I can have some load. It goes out to memory. It misses. I can have an instruction that's dependent on that load. And the next 100 instructions could all be a bunch of register operations that are already ready. And you can just still be sitting there going, I'm waiting on my load. I'm waiting on my load. I'm waiting on my load. Right? Could be that for 100 cycles. Right? So the readiness of your operands is completely unknown. You'll be told when they're ready. They're ready when they're ready. Right? Different execution model. Right? We don't have this nice ordering. It's like, oh, we know the things in front of us will finish, in front of us, and we can schedule. No. They're ready when they're ready. Okay. We need to know where we are going to be writing our result back to. Right? Not very useful. Again, these are all going to be physical register identifiers. And similarly, if you have a third source, which is an immediate, you would also presumably encode this either here, or you could think of the immediate as part of the instruction. However you want to think about it, doesn't really matter. But this is all of the information needed to understand what you need to do, what you are going to need to do it on in terms of locations, but not necessarily in terms of values. So that we'll see a little bit later. There are multiple implementation options. I I could store the actual values along with the identifiers here as they become ready. There are reasons you might want to do that. For instance, maybe one of these is going to be ready much earlier than the other one. It may actually make sense to have it sit there in the queue for a while and then send the whole packet off directly to the functional unit. Some of this also has to do with whether or not these issue queues are distributed close to the functional units or they're centralized. If they're centralized, you probably don't store the data there. You read them from the register file on your way to the functional unit. Implementation decision. Both have been built. Right? Both of these models have been built. They have some trade-offs in implementation, but they're logically equivalent with respect to scheduling. Okay. So if both of our sources are ready, again, immediate is ready immediately at the time I put this entry in, so I don't need to track if a ready bit for there. Just add those two together, they're all ready. You can imagine a physical table implementation of this, right? Every one of these is something I can access and write or read as a RAM entry, right? And all of this is coming out just with an AND for every one of these, hardwired out to some ready bits for each entry. And later we'll see that there is CAM logic associated with the matching of your identifiers, right? That is going to enable you to figure out whether or not you should set the associated ready bits when things become ready. Okay, so one entry, your queue is going to be dozens to hundreds of these. Probably more like dozens. CAMs are not the world's most scalable objects. Okay. All right, so again, content associative, content addressable memory are a good way to build highly associative structures. If you're looking to build an SRAM style CAM, there are also TCAMs. We're not going to worry about TCAMs here. Ternary CAMs, which support wildcards. You don't need wildcards here. These are all exact match. But your basic CAM is 16 transistors per bit versus an SRAM of 6, right? So, more than twice as big in practice. They also have a lot more wires, and actually figuring out the read side from the CAM can have its own output scaling as well, right? Because you have to collect all these hits. You can often do RAM access into a CAM, right? As you would in particular in the issue queue, right? Ultimately, there is a bit that is being stored, right? The rest of that is comparison logic. There are some more efficient ways to build CAMs if you're looking at alternative technologies. That's the good news. You can do things like a 2T, 2R CAM. Bad news, those have wear out of like 10 to the 8th, so you wouldn't put them deep in your system. Yes? So a CAM, right, has an identifier and a value associated. So you might actually, so if all you care about is a match, you could even have a null data field. So actually what you have here is actually a degenerate form of this. All I care about is the identifier. So all I care is, so let's say this is P5, physical register 5. And let's say that some instruction has just produced a value for physical register 5. Well, which of these instructions in this issue queue are now ready? How do I find that out? I need to find all of the things that have a physical register 5 field. So I'm going to build a content addressable memory where I can broadcast P5 across all of the source fields, do a comparison in parallel, get all of the hits where it is a match, and set the ready bits accordingly with a CAM. Now, more broadly, I could have some data associated with my match field. So a lot of CAMs. So for instance, if I wanted to build a very highly associative structure for a TLB, right? Let's say I have a fully associative TLB. It's got 32 entries. I don't do that, with standard set associative logic, right? I do it with a CAM, and there I'd have my tag would be my match field. My data would be the actual block, right? Yep. Right. You broadcast an identifier and you get back all of the things that match the identifier. So as I said, RAM is a lot denser, and a lot of the things we're doing are access based on address, right? So if I have a load, I want the contents of memory at address. The semantics of that are RAM, right? If I want, give me all records that match this identifier, those semantics are very CAM in nature. I can implement it by a sequential search through some RAM structure. I would not want to necessarily build a CAM with millions of entries, right? Again, broadcast, physical wires. I do not want to connect electrically millions of things to a single wire. That's not going to actually work very well. You'd want to have some sort of search structure built on top of your RAM if you're doing that. Yeah, it'd probably be. Yeah. So I mean, think of your classic algorithmic search, right? So CAMs are useful, but they're expensive, right? They're power hungry. They're not very dense. They don't scale amazingly well, right? So your RAM structures are very, very large, but finding a needle in that haystack, well, you have to go and look for it. CAM structures, you can find things very easily as long as there aren't that many of them. Okay, so what do we have to do in dispatch? Well, we just have to populate the ROB and the IQ and potentially the LSQ entry. Okay. So the resource demands of dispatch are basically available slots. If the ROB is full, stall. Pretty easy. If the IQ is full, stall. If you are a load or store and the LSQ is full, stall. Right? As long as there's an available entry, cool. Right? If they're not full, find an empty slot in the IQ. This actually does require some finding because, again, they will enter and leave in no particular order. Right? So you have to actually sort of figure out where in the IQ you're inserting it. I'm not going to go into any particular detail about that logic. It's not too bad. The ROB is trivial. It's a queue. It's a FIFO queue, right? Where do you put it in the FIFO queue? You insert at the head or the tail, depending on which way you want to claim it's going. Okay, now some of the things that we are putting in are already ready already. Say that 3 times fast, right? So I need to have an initially valid state for my ready bits, right? So I'm going to have a table that tells me what physical registers are currently defined, right? So it's just a 1-bit wide table. So 1 bit by number of physical registers. So I just look up the physical register number and I say, are you already ready already? Again, say that 3 times fast. Okay. We are then going to clear the ready bit of our output register. Now, you could have already done this when you added it back to the free list. It is certainly sufficient, if not strictly necessary, to do this now, right? It is certainly the case that whatever register you are producing at the time that I'm throwing you over the fence into the out-of-order execution engine has not actually been produced yet, right? You could be more aggressively trying to clear these, again, as you free the registers and put them on the free list. So you could have an invariant that nothing on the free list has its ready bit set in the first place. But it is sufficient to be lazy and do it now. Right? So if your inputs are already ready, mark them as such. Your output is definitely not ready. So anything that comes after you, remember dispatch is still in order, anything that is after you must read your output as not ready. Right? All that's really going down. We're just maintaining an invariant. Okay. We write the instruction data into the allocated IQ slots. We saw those fields. And we have to tell it which physical registers is dependent on which destination, how old it is, right? We allocate similar space in the ROB for all the metadata that is going to accrue along the way, right? And the load word and store word, you should at least start thinking about the fact that even if in these examples we have not done so yet, should be split up, right? We really want to think about the load word and store word as an address calculation and an access to memory and start treating those separately. Right, so the address calculation is a stand forward. It's literally an add immediate, right? The only thing that's a little funny about that add immediate, if it's an effective address calculation, is, well, what was the destination? The destination, you can imagine, again, some sort of virtual, the EA register. Right? Imagine that you have an extra architectural register that doesn't really exist called effective address. If you split every load and store instruction into a 2-instruction pair thusly, all the rest of this logic will follow correctly. Okay. So the actual access will go in the LSQ. So obviously things in the LSQ will actually be dependent on things in the IQ. Right, so there'll be dependency via that effective address on whether these loads and stores are ready to go. So some of that dependence tracking will go there via the particular physical register that is going to contain the effective address. Again, since the effective address is never actually really written, you could squint and bypass that and not actually allocate a physical register. So that's why I'm sort of hand waving a little bit here. There are details that you could do a little more efficiently. We'll show you some examples in recitation of both approaches, right? But again, just remember that logically they have two different things that need to happen for load and store. Okay. Now the load store queue is, we'll go into this in some detail, has both associative and ordering structures, right? So the load store queue does actually care about the order that the things are maintained within it. Again, we need this because we don't actually know the addresses that are going to happen here. We're going to need to make sure that those resolve properly. Right, so the load store queue is actually going to handle, among other things, forwarding between our loads and stores. Right. Okay, so without doing the effective address split, because, well, that makes more lines on the slide, let's go for dispatch. Let's go with the simple version of dispatch where we're not doing the split. Okay, so they've already been renamed, and into the issue queue they're going to go. So we're going to take this load word, and we're going to start populating all the things that are needed in this entry of the issue queue. Okay. And again, we fudged a little bit on where the immediate goes. Let's not worry too much about it. Again, if it had been broken up into an effective address calculation, this would be an add-on. So it's a load word. Source 1, right, that's an immediate. Source 2, this is register P1. Destination is register P4. It is the oldest thing we have. We're going to read the contents of the register ready table. If it is the oldest instruction around, maybe we just had some sort of pipeline flush, then clearly everything is ready already. We'll start with that. But what we will do is mark its output as not ready, right? I'm going to produce P4. P4 is definitely not valid yet, right? I have not actually done the load, so how could you read from P4? Anything subsequently dependent on P4 is going to have to wait. Okay, ADDO is going to go down the pipe. Again, this is still in order at this point. In comes ADDO. And it's going to have these sets of dependencies. It's dependent on P4 and P2. It's going to read the current versions of ready bits. See, P4 isn't ready, but P2 is. I'm going to write into P5. I'm going to set P5 to no. Note that this is maintained, right? So everything is good. Okay. Rinse repeat for these others. Store word, source P5, source P1, age, no destination. Again, all the read after writes still maintained. Yes.
So when it comes to like, because like, you know how like in the we had like.
Mm-hmm. Yep.
What I'm wondering is, do you need like a pipelining diagram like on the side of this to figure out when P4 gets free?
No. So the whole thing with dynamic scheduling is that it's basically an interrupt-based model, right? So what we'll see is that things will be released from the issue queue as a function of the readiness of their source fields. So what's going to happen is when this load word is dispatched, is issued, right? So when I actually say, oh, I'm going to actually go do this load word now, at that time, and only at that time, do I have an understanding of when P4 will be available, right? And then I will broadcast this information about the availability of P4 to all of the instructions that might be waiting on P4. And if they are ready, then in the next cycle, they can issue as well. So nothing is executing it. This is all just populating the table, right? So no execution is happening yet. Who knows? We don't know. We'll get there. Right? We're still just transitioning from the front end to the middle end of our machine. Or we're just setting up all the state to do the execution. No execution has actually happened yet. I know it's a lot of lead up, a lot of setup. Right? Okay. Okay, so same process. Again, fairly mechanical. Again, that's why you're going to program it. Right? In your first programming assignment. Okay, same with the ADI. And there you go. Okay, BNE. Second verse, same as the first. All right, so if we had a 6-wide machine, we'd do all this in 1 cycle. If this was a 1-wide machine, we'd do all this in 6 cycles and in between, as you would do.
So, like, what's the data? Put a wire.
And so we're going to be constantly reading. So the contents of this table should be the same as if I had done each of these one at a time. Right? So if this was P4, right, that I was dependent on, then I would read it after this had been marked as not available. What you will see later when we go to issue is that all of the things that are dependent on P4, and this is why we need the CAM, are going to be woken up at the same time. Something you always assume negative, you read from the contents of this table. Yep. So if something has marked it as no, then it's not ready now. And it'll be ready once the thing that is currently producing it has been scheduled. Right? So you can assume some pipelining. So that this is the nuance you're going to get with selection and wake up, which are the 2 stages in issue. Right? So it'll happen in the next part in the out of order. Right? But what you can assume that there's forwarding within the pipeline that actually produces, this value. So you can launch things one after the other, right? But you're only going to launch them when the value is actually in production, right? Because otherwise it couldn't possibly be there for you, right? Mm-hmm. In this particular case, a lower number is older. Yeah. Again, this is not strictly necessary, but you probably want some sort of priority metadata in any implementation that you have, right? This could be some other value other than age. Without loss of generality, age is a reasonable prioritization metric that you could have to ensure that your queue does not clog indefinitely. Right. Okay. Okay, so this gets us to here, right? So now at this point, we have fetched and decoded and then renamed our instructions. We have sent all these renamed resource requests into the IQRB and or LSQ, right? So far, nothing has actually happened, but now everything is ready to happen, right? We have now populated all the structures required to perform our dynamic scheduling and our out of order execution. Okay. So let's go to, boop. Yep. Okay, so let's pop over to 670-5591. Let's ponder a couple of questions about some of the semantics that are going to happen. One of the answers is actually was already on the slides that you saw if you read it. We'll see. We're going to ponder some of the semantics of things that are going to happen during out of order execution in order to keep our ordering straight. You still logging in? Anyone? Okay. Let's get started. Anyone still logging in? Still logging in? Bueller? Got it. Okay. So again, recall that renaming took care of most of our problems for register dependencies. Let's think a little bit about the logistics of loading and storing. Mostly a question of semantics. Once more unto the breach, my friends. Henry IV, right? The Bard. Okay. Okay, stores can be sent to the D cache when? When is it going to be legal to present our good friend, Mr. Store, to the D cache? Again, we renamed our registers. We have not renamed memory. When can we present our store to the D cache? Okay, so we could not possibly do it before this point. We wouldn't know what to do it on or where to put it. But that would be what we like to call bad, because we couldn't unroll it, right? The time we know the effective address and value, we don't even know if this is a correct path instruction. Right? You may, in fact, never execute this store at all. It could be on the other side of a branch. Right? You have no ordering. So this is when you could put it potentially in the store buffer, but not when you can present to the D cache. You cannot modify externally visible state until you actually know that effects are going to occur in program order. Okay. Similarly, this is insufficient, right? Just because I'm the oldest in the load store queue doesn't mean I am the oldest in the ROB, right? So again, there may be a branch in front of me. Even if I'm the oldest memory operation, my entire contents of my LSQ could be on the wrong path. The same logic goes there. This is a perfectly fine answer. You could build the structure that way, but this is a better answer because a buffer buffers, right? So it is eligible to be sent at commit. So when I'm the oldest instruction in the machine, I can take it from the store buffer, retire it into the D cache, but I could also be lazy, right? Nothing actually changes in my program semantics as long as I'm actually going to, read from the store buffer, right? If I'm actually using the store buffer, I'll still get the right up-to-date value as long as it will eventually drain, right? So it's sufficient to eventually drain. Anyone who answered yellow, that's fine. You have a pretty good understanding of what's actually required, but you can be even lazier. So time is a wonderful thing that we can still play with, right? So at or after, either of these are pretty good answers. This is the necessary requirements for it to do anything at all, but we can't put it to the D cache yet, right? This is when we would be able to put it into the store buffer. Okay, so now that we've thought about stores, your next question is going to be about loads. So start thinking about when loads can go and start phoning a friend. So talk amongst yourselves. I have no idea what these points are based on. So, time? Okay. Well, there we go. Okay, so discuss this one with your friends and neighbors. Again, at least your neighbors. They might be your friends. Maybe they're not. I don't know. I don't judge. When can loads be sent to the D cache? Okay. So much like an old Bob Dole joke, it depends. So let's take a look at these different options, right? And the point of this, A, is that load and store semantics are complicated. We're going to spend a little time in load store queue. And B, that we're going to show you two different ways of doing this. Right? There are going to be two different types of schedules that we're going to produce with aggressive and conservative load store scheduling. You will be expected to be able to do them both, right? And the reason is, if I wanted to wait on my load reading data from the DCAS, so again, it's a read. It doesn't modify state. It does not modify architecturally visible state. Modifies microarchitectural state, hence Spectre and Meltdown, but it does not modify architecturally visible state to do a read, right? Reads don't modify things, right? So unlike the store, where I am bounded and could not possibly modify this state because I wouldn't be able to undo it until quite late, the load I can do earlier, maybe, right? And that has interactions with my ability to get some ordering wrong and recover from it, right? So if I read a value from memory and say, okay, I'm going to read this value, just go to the cache, get the current value. And I'm going to look in the store buffer as well. And obviously, if there's a newer value in the store buffer, I'll take it because that preserves my appropriate ordering semantics. But if I've done this and I haven't actually resolved the addresses of all logically older stores, it is possible I have read the wrong value. There might be a store that has yet to actually store its value, which will store it to the location I just read from. I could be misspeculating. Okay. In practice, most loads and stores do not point at the same address, right? Memory space is large. Yes, your program has particular dependencies. It's presumably acting on some set of data structures. But if I were to just take loads and stores at random, most of them don't conflict, right? The odds are actually pretty good that this load is in fact not dependent on most of these older stores. And waiting could be quite a wait. And again, that load waiting stalls everything behind it. So I want this load to go. The store doesn't stall things behind it. I already have the value. Nothing is waiting on me to produce the value. I already have the value for the store. I just need to put it in a buffer and not forget the order. Stores don't cause terrible pipeline hangups. Loads do, right? Everyone can be waiting for that load, right? So I want to get this value as soon as possible, right? So the question is mostly, how conservative do I have to be in terms of issuing it? Now, even if I am going to be maximally conservative, right, then it actually turns into this. And actually, even this is slightly misworded, but it's all the stores are actually what I would need to know, not all the memory instructions. I should have been a little more careful there. If I know the addresses, the effective addresses of all older stores, then I can understand whether a collision will happen. Then I can non-speculatively get the right value from memory from either the store buffer if one of the stores matches, or the data cache if it does not. There's actually sort of a 6th option here, but we haven't gone over multiprocessors yet. So let's hand wave wildly at consistency models and the ordering effects of buffering in the first place. For everything that we know in terms of just at least the thing being right, the answer is going to dwell on this. So you're going to look at both a conservative and an aggressive load store ordering schedule, and you'll implement them because they are very programmatic. Okay, cool. But more on that on Thursday. Okay, but now that we know that when it comes to memory operations, there are a couple of different options we'll see here. Let's go over at least the general case of how to proceed now that all of the structures have been populated. Okay, so the out of order model that we're going to look at, and you can squish some of these together just as you can with any other pipeline. But broadly speaking, we're going to worry about issue That's going to be sort of the most novel piece, right? So when do you actually get scheduled, right? There are a couple of different options in terms of where you actually get the values for your registers that you need, right? We'll talk about that, but without loss of generality, it is perfectly reasonable to imagine you are scheduled, pick up your registers on the way to execute, and then write them back into the physical register file. These two definitely happen thusly. For the purposes of a lot of our scheduling, in order to keep the pages small, we may often squish these first three stages together and just imagine that issue is execute is register read. Okay. Again, implications on cycle time and scaling, but logically, it's the same as if I split my pipeline into deeper, deeper, deeper. Right? There are a set of things that have to happen. All of these things have to happen, and in this order. How many cycles it takes to do so, pick your clock frequency. Right. Okay. So we're going to dwell mostly on the issue portion. And then these are operations on the instruction queue. Again, we'll talk about the load store queue separately and later. Right. So there are two phases to issue. Right. So issue needs to first take the instructions that are currently ready, and among those instructions that are currently ready, send them off for execution. Right. Now, just because you're ready doesn't necessarily mean you will actually issue in this cycle. There could be more things that are ready than I have the availability to send out. There could be a resource dependence challenge, right? So maybe I can send 4 instructions per cycle, and there are 4 instructions ready to go, but they're all loads, and I only have 3 memory ports. Right? So that's Select's job to figure out, are you in fact ready to be sent down the pipeline? So this looks to some degree in terms of its job, not terribly different than, say, hazard detection of can you advance down the pipeline, is everything ready to go? But the way that it's working is obviously going to be very different because this is a dynamic scheduler. We're not doing this based on sort of looking down the pipeline at older instructions. We're looking at the input side of the instructions that are sitting in our issue queue. So remember, everything in the issue queue has not yet executed. Right? The ROB has all instructions that have not yet committed. The issue queue only has the ones that have not been sent out to execute yet. The IQ is going to be smaller than your ROB. Okay. Now, because we have a pipeline, and we would like to be able to issue instructions that are dependent back to back under assumptions that pipelining forwarding will work, like add to add to add to add should work just as well in out of order as it did in our in-order pipeline. We also want to have some wake-up logic so that in the next cycle, right, the dependent instructions will be considered ready. Right? So we're going to take the ones that are actually ready right now, select some of those, remove them from the issue queue, send them down the pipe, and mark all of their dependents as good to go. Right? There are some asterisks here. If I have some unit that, say it's an integer divider, right? I know it's going to be 40 cycles before actually any of its dependent things are going to be ready to go. Do I actually wake up its dependents immediately? Probably not. Or I have some sort of counter mechanism here that'll count down automatically to, rather than just a bit that I'm setting. We are going to not worry about that level of detail, right? There are lots of optimizations you can do for things with some longer latencies that you want to send things behind. Even if you imagine the difference between a load to a use, you would actually not want to immediately send it down the pipe. You'd want to say 3 cycles from now, this value is going to be available. Right? But again, without too much loss of generality, we're going to worry about this and issue aggressively. Any questions before we go into the details? Select, wake up. Select from those that are ready now, wake up so that they will be ready next cycle. Okay. TikTok. So our hardware is going to have plenty of forwarding available, right? Now how that manifests, you've got design options. if you, and we will actually read Guri Sohi's RUU paper. I mean, that was a one wide out of order machine. So it just had one bus that all the outputs were coming back on. Again, sort of inspired by Tomasulo from 20 years previously. Whether or not you want to be forwarding all of your data to all of your potential functional units, probably not. You don't probably need to forward your floating point values to all of your integer units or your address generation units. So there is some clustering and loose partitioning that happens in real designs. We're not going to worry about that at this level. Right? We're going to have a mostly centralized model. You can figure out how you would want to decouple and distribute it as an exercise for the reader. Okay. The only thing I want to hammer into your head here, because people do sometimes get it wrong, the right back here is to the renamed physical register file. Right? So everything here in this lovely, slightly burnt salmon color, right, is happening in our renamed physical register space. There are no architectural registers to be found. T0 does not live here anymore. Okay, so let's take a look at issue. Right. So let's say we have our machine. We had populated this entire table, right? And let's say that we in fact had already issued a load word, right? It's off doing its cache miss. It's still pending. And yes, there are dynamic things like cache misses, which would cause you to have to, stall further down in the forwarding or actually cycle things back in and reissue them again. Which of those is better? We're not going to worry about it. Right? Implementation details. There are lots and lots and lots of potentially different designs for how to do this, depending on your constraints. Okay, but if this is the current state of R already issued, this is an empty, so imagine that there's a valid bit here, invalid, right? Already sent, not there. Okay. So this is the current set of the 5 instructions that are actually in our issue queue, right? We would look at these and we would note 2 of them claim to be ready, right? This is valid, this is valid, this is valid, this is valid. These are good to go. Right? So imagine that there are literally AND gates hooked up to all of these pairs of bits, and they're just sending some signals out. Put me in, coach. Yeah.
So why does
it should be freeing up. So P1 wasn't freed up. P1 was ready already. P4. So again, this you can imagine that it was marked as ready speculatively, and then there was a cache miss, and so there's still variable behavior that you'd want to account for in a real version of this, right? So let's ignore the load word for the moment, right? So you can imagine perhaps that tag lookup, right, happened in a single cycle, and it noted that it was a miss, and it went back and said, oh, actually, there's no P4, right? So don't worry about it. For the moment, it's not there, right? Okay, but if these are the 5 that are there, what's our selection logic going to try to do? Right? It's going to try to select things that are ready and issue them, right? Send them out to the functional units. Let's think about the constraints that it's operating under. The first question is, how wide is our issue? Right? So as I mentioned a couple minutes ago, Guri Sohi's paper from 1987 was a 1 wide out of order machine. So the chief constraint there is it would only select, well, one of them. It's a 1 wide machine. Right? If we have a 2 wide machine, they could both go. Great. Assuming I have 2 adders. If I have a 2 wide machine, I have 2 adders. Adders are cheap, but you get the idea. Right? So depending on what the instructions actually are in terms of a resource request, how wide I can actually do my parallel issue, right? Those are going to constrain how many of these ready instructions actually go. If I only had a 1 wide machine, or for some bizarre reason I only had 1 adder, right? I would probably want to pick the older instruction over the younger instruction, because this will clear my queues faster, right? but both of them would be perfectly legal to take. Right? All right. So they're ready. Yay! That is what we want. We want lots of ready instructions, right? Again, the right way of looking at this is that out of order instructions execution's goal. Again, I can't show you, in any readable format, a say 64 entry issue queue, but is to get a big enough window that you can find things that are in fact available to issue at the same time. And if I look at bigger and bigger chunks of my program, the odds increase, right? So if I look at 64 instructions at a time, hopefully I can find 3 or 4 of them that I can do right now. You can already imagine this is perhaps not the most power and energy efficient thing that the world has ever created, right? But it does get us our performance. Okay. Because we are in fact looking at all of them every cycle. It's an associative search. Okay. So selection is, we're gonna grab both of these. Wake up is that we're gonna take a look at what their destinations are, P6 and P7. And we're gonna set those to all of the ones that are dependent on them, right? We're gonna have to wake them up. How does it work? Cam search. Yes?
But store depends on store uses P1.
But P1 is not being written, right? We're worried about the destinations here, P6 and P7. P1 is ready. Yeah. Storeward is stuck on P5. Right? That's why it's not ready. So this is ready. It's fine. Yeah. We have an immediate. We have P1. We're good. Yeah. Again, if I'd split this up into 2 instructions, there'd be an add immediate instruction here, and the add immediate would be ready to go because all I need is P1 and a 0. Right? But I didn't. We'll do that on Friday. Okay. So we need to wake up the dependent instructions. How are we going to do that? We're going to broadcast the P6 from here, broadcast the P7 to here. How many things do we have to broadcast it to? Well, how wide are we? If we're 4 wide, we would need to broadcast up to 4 values to both of the register source fields. Right? Again, immediates we don't need to worry about. Right? So we are going to send 4 broadcasts for our 2 outputs. Right? If we were 4 wide, this would be 8. If we were 6 wide, this would be 12. It's just 2x. Right? And we're going to broadcast this and use the CAM functionality of our issue queue to find all of the source 1 and source 2 fields that match these values, right? And remember I said CAM was 16 transistors? Well, actually, that's for just 1 lookup. So that's actually going to be bigger per cell as a function of the width of the machine. Again, you can begin to understand why your issue queue is not going to scale indefinitely, right? And why some of these lookups are expensive, right? I am taking a big metal wire, running it to every cell and hooking it up to comparator logic and repeating that the number of times that I have IDs that I need to be sending for my issue with, right? This is expensive, right? If I want to get this done in a cycle, it only can be so big. But logically, pretty straightforward, right? So broadcast P6 and P7, right? Any of you need P6 or P7? You need P7. Any of you need P6 and P7? No, we're good. And so we'll mark this as a yes, so that in the next cycle, that branch is good to go. Right? So we can think of these as the tick and tock within a single cycle. So I'm going to take everything that is already ready, select it, take everything that is going to be ready, and that's going to be written when the clock comes by. That value will be bloop, set thusly for the beginning of the next cycle. Okay, select and wake up. Okay. Okay, so let's say that our cache miss has resolved. Right. And variability does still happen. Right. So here we go, resolved our cache miss. How exactly do we do that? We're not going to dwell on the details, right? It's complicated. There are lots and lots of policies. Many papers have been written about what the best way to do it is. But logically, we certainly could wait, right? There's some way to wait. Now we look at the set of things that are good to go, right? We have an add. This is going to be good to go. We have a branch. That's going to be good to go, right? These are ready. Assuming again, what we can do too wide on here. These will be going to be good to go. We're going to mark their dependencies. Boop. Select wake up, select wake up, select wake up. Now, at the same time that this is happening, dispatch is going to keep feeding new instructions into this issue queue. As you note, since they leave, not in the order they were written in, the new entries will fill in wherever there are blanks. This structure will very quickly not be particularly ordered, right? It's going to be arbitrarily fragmented. Right? So again, dispatch does have a little bit of work to do here to actually figure out where the open entries are. You can do bitmaps, other sorts of structures to get it written to the right place. Not too big a deal. Just some demuxing. Okay. Select wake up, select wake up. Boop. Great. Okay. Now, I said that there were some options. I'm going to discuss at least two. These are two sort of classic ways that that things have been built. Okay, we got 5 minutes. That's about right. So in the order that I showed there, you know, you issue, then you do the register read. There is a bit of an alternative. So we can't do our register read at decode like we did in our in-order pipeline because, well, what we are dependent on is physical registers, not the architectural ones. So we got to do our reading to the renamed registers. So option one, this is what was used in the P4 or the MIPS R10K. Right. You keep your issue queue reasonably small. Right, it just contains IDs, and all of the actual reading of physical registers is going to be from the physical register file or from forwarding from a functional unit based on the physical register name further down the pipe. Right. Option two, right? Because the physical register file, and when I say maybe large, you know, it's large, right? If I want to have, you know, hundreds of instructions in flight, 2/3 of which define a register, then I need a lot of physical register files, or I fundamentally under-provision my machine, right? And so that register file read can take a while. I mean, it's pipelined, but it can take a while. And some of these registers may have been ready for a very long time before the one that finally released you, right? So it turns out that frequently, you're only waiting on one of your two sources. Right? They don't all arrive at the same time. You have asymmetries in the depth of your program dependence graph. So if I extend my issue queue with space to actually store the value itself, right? So then at the time that something is made available, right? Then I can, as was done in the Pentium Pro, the Core 2, or some of the later descendants in the Core i7 series, I can just hang around to any value as it becomes available. Now, again, this one's implemented in distributed fashion rather than centralized. Don't worry too much about that. They have multiple issue queues for each functional unit. You know, same logical stuff applies. And here, again, you can still get it through forwarding, right? If I issue an add to an add to an add to an add, forwarding is still going to be where that's coming from. Or for any of the values that were already ready, I just initiate that read as soon as it becomes ready at dispatch. I start that read, and I'm going to write that into the issue queue. Right? And as soon as that read has finished, then I'm going to mark it as ready, and it's just going to sit there until I actually decide to use that instruction. So different structures, different trade-offs. If you really want to dive deep into sort of this level, you can go look at some of my graduate slides. But suffice it to say, you have options, right? no matter which one of these you choose, logically, you will have read the renamed registers before you get to your functional unit, and forwarding of some form will occur, right? No forwarding, then it's still not going to be able to issue anything with any speed, because I would issue and then I'd wait, and it wouldn't be actually ready yet. I'd wait till it's written back. That's going to take several cycles. I want to issue things back to back. I don't want to be slower in dependent to dependent instruction sequences than I was in my original design. Okay, so we haven't gone into all of these pieces yet, but this is where we will pick up on Thursday. We will go into more detail here, right? And there is some ordering that's happening in here, so that's why I've marked it a bit gray. Again, the ROB also is an ordered structure, right? Even though the reads and writes into it are not. And these are all the pieces we're going to start talking about on Thursday. Again, be on the lookout for Project 1 will go live tonight. Again, you won't be able to finish Project 1 without the information from Thursday, but you can start reading it. It'll be a few weeks. It's a lot longer than it takes to do it.